I'm sure everybody in the audience has heard about the corona in black hole X-ray binaries. So I will ask the rhetoric question, what is it? Okay. First, let me tell you what our community thinks it is. I will present, therefore, the standard picture that our community has about the corona. And the corona is, although everybody knows, I repeat it, the place where the hard X-rays are produced in black hole X-ray binaries. Dimitris Kanzas referred to it in his talk in the previous session. And then I will point out inconsistencies that exist in this standard picture. Okay, what's the standard picture? First, standard picture regarding spectra. The standard picture is based on two strong beliefs that our community has. And I would go as far as saying that they're not only strong beliefs, they are hard party lines. If you don't obey the party line, you're out. So really, our community has these strong beliefs. Belief number one, the power law X-ray spectrum, which is power e to the minus gamma. Remember, gamma is the exponent of the hard X-ray spectrum. I will use it again and again. This hard X-ray spectrum is produced in the corona, which is the hot inner flow, ADAF-like, by inverse Compton scattering of soft blackbody photons that are emitted from the accretion disk. This is the standard picture, and I have nothing against it. Okay, I will tell you where I object. So continue. Here it is, schematically, the Shakura-Sunyaev disk outside, the hot inner flow, which is what we call corona, and the black hole. So soft photons from here enter the hot corona, get Comptonized, get upscattered, Comptonized that is, and escape. And this is what produces the power law spectrum e to the minus gamma. Now, standard picture regarding timing. Now, we observe that the hard X-ray photons come later than the softer ones. In other words, there is a time lag between the hard and the soft photons. The hard photons come later than the soft ones by a few milliseconds. And belief number two says that these time lags of the hard photons with respect to the softer ones come from propagating fluctuations in the accretion flow. And I will explain what that is, back to the schematic. Now, it is assumed that this corona does not have uniform temperature, but the temperature increases as you go in. Oops. What is it? The temperature increases as you go in. So first you see the softer, the little upscattered photons. Later on, you see the harder photons. Therefore, that explains the delay. This is the standard picture in our community. Okay, I have no objection to this either. It's fine with me, and I'm sure it's happening because I cannot imagine an accretion flow without fluctuations. But the two mechanisms, the Compton scattering in the corona and the propagating fluctuations in the flow, do not talk to each other. In other words, no correlation is expected between the time lag that comes from the fluctuations and the power law index gamma. They are two different mechanisms. Gamma is determined from the properties of the corona, optical depth, temperature, while the T lag from the properties of the flow time scale, the origin of the fluctuations. So the two mechanisms are completely different and don't talk to each other. So no correlation is expected. However, the two are correlated. A nice correlation that I will show you in the next slide was found by Pablo Reg and me in GX339-4. And here it is. Lag spectral, the lags as a function of gamma. The source GX339-4 starts at quiescence, goes in black symbols, goes to the hard state, red, and goes to the intermediate state as the outburst progresses. So the blue dots are the data, and the other symbols, the X's, are our models. So you see that we fit quite well this correlation, while in the standard picture, these two quantities should be uncorrelated. Okay. We have explained this correlation by assuming Compton scattering in the jet. In other words, what we now call corona includes the hot inner flow and the jet. So the corona is not, and I will explain it better a little later. So the corona is not just the hot inner flow, but it includes the jet. So the Comptonization determines the spectral index gamma. The size of the jet determines the T lag. And since both gamma and T lag are produced by the same mechanism, Comptonization, it's no surprise that they are correlated. Well, before, two totally unrelated mechanisms were producing the two. Okay. It is generally assumed in our community that jets are like fireworks. They are beautiful, but they are useless. So I will try to convince you that this is totally wrong, and that jets must be a part of the corona in black hole X-ray binaries, must be a part of the corona. So you have already seen very briefly the explanation of the T-lag gamma correlation. I will discuss a few more correlations. And here is the picture with the jet. The Shakura-Sunyaev, the Shakura-Sunyaev disk, the hot inner flow, and the jet that emanates from the hot inner flow. Notice that there is no boundary between the corona, the hot inner flow, and the jet. So if a photon starts here and random walk here, it's highly likely that it will go in the jet and get scattered in the jet also. So you cannot avoid having Compton scattering in the jet, even if you wanted to. An inference. I said it already. The base of the jet engulfs the hot inner flow. So thus Comptonization in the jet is unavoidable. In other words, most photons that enter the hot inner flow cannot escape without traveling in the jet and being scattered there. And in the scattering process, the photons forget where they started. After a few scatterings, they do not remember where they started in energy and in space. Thus, it's the last scatterings, the last few scatterings that determine the spectrum. In other words, the scatterings in the jet fix the observed power law index gamma. No matter how many scatterings existed in the hot inner flow, it is the jet that determines gamma. It's the last few scatterings that determine the spectrum. Now, you may say, well, could this correlation be just a peculiarity of this source GX39-4? And the answer is no. More or less do the same. All the sources do more or less the same. And here is all the sources. Plot T lag versus gamma and a correlation. Now, it's mathematically accepted. This correlation is mathematically accepted, but very unpleasing. Look at the scatter. A mess. So we looked at how this correlation changes with inclination of the source. So low inclination sources obey this curve, and high inclination sources obey the red curve. and all others are in between. So now we understand what this scatter is. Each source has a nice correlation, but all of them have a scatter plot because they have different inclination angles. We see them, others we see face on, low inclination, and others we see edge on, high inclination. Okay. The T-lag gamma correlation that I showed you is quite stringent, and it's explained naturally with the jet model. Are there any other observational constraints for the jet that the jet model explains? The answer is yes, else I would not ask the question. And I will mention only a couple because there are more, and they are published, so you can find them. So next is the time lag versus Fourier frequency. It's a power law, nu to the minus 0.8. This is an observation. This is observations. Now, here is a schematic of the jet. I represent the jet as three regions, R1, R2, and R3, increasing in size as the jet increases outwards. If the photon scatters here, there is a time lag T1, and Compton scattering acts as a filter that filters out all the high frequencies. So all the frequencies higher than 1 over T1 are eliminated. Here, all frequencies 1 over T2 are eliminated. Here, all frequencies 1 over T3 are eliminated. And therefore, you get a power law as observed, nu to the minus 0.8. Okay. In 2015, Altamirano and Mendes published another correlation, the phase lag, which is equivalent to the time lag, versus the cutoff energy at high energies. And within days, Pablo and I fitted the correlation with our already existing models. So I hope I have convinced you that the jet is not just fireworks emitting radio waves, and it seems to play a major role in the observed phenomena. Thus, I will discuss now, and I'm closing very soon, how the jet illuminates the accretion disk. The jet naturally illuminates the accretion disk, the Sakura-Smirnoff disk, and therefore there is no need to invoke lampposts. What our community does is to invoke a lamppost, and on top of the lamppost, a point source that illuminates the disk. Why use all that? You have the jet to illuminate your disk. So I will show you that the spectrum that comes from the jet after Compton scattering is anisotropic. Here it is. The jet, the photons that go towards the observer have a harder spectrum, and the photons that go towards the disk have a softer spectrum. This is because the jet is elongated and it has bulk flow. And last plots, we give the fraction of photons that hit the disk depending on what height they were emitted. So most photons hit the disk being emitted close to the at the bottom of the jet, and as the height increases, the ratio goes down. This is for different parameters. So now we have the source that illuminates the disk. And in closing, I should say, just to be a little provocative, especially for the young guys, and here I want to say something that I ought to say after Dimitri Kanzas's talk. I was impressed that he dared make a prediction for GX339 minus 4. So I say that all self-respecting models must make predictions. Why? So that they can be shot down. Otherwise, we don't learn anything. If a model cannot be shot down, it can live forever and it teaches nothing. So we have made a prediction, and this regards the break frequency in the radio spectrum. Break frequency in the radio spectrum is the frequency at which the spectrum goes from optically thick to optically thin. Radio astronomers, therefore, are welcome to check our predictions, which I will show in the next slide, and possibly shoot down our model. There is no reason in working on a model that is completely wrong. And as Martin Rees has said, it is more important to be stimulating than right. As long as we stimulate work, we've done our best. It doesn't matter if our prediction was right or wrong. It's better to be right, but even if it isn't right, if it stimulates research, it's excellent. And last slide and closing, here's the prediction. These are the points that I showed you before in the correlation of GX339 minus 4. This, we predict that in the rise of the outburst, that is at the beginning in quiescence and the hard state, the break frequency will increase, will have a positive correlation with gamma, and it will have a negative correlation with gamma in the hard intermediate state. This part, the green part, has already been confirmed. So what is needed now is in a new outburst of GX339 minus 4 to observe the radio spectrum and determine the break frequency. We predict that it will be increasing in time. As the luminosity increases, so will the break frequency. And I'm closing by showing you the last slide. Thank you very much.
Thank you very much for this very interesting and provocative talk. So we have some time for questions. Yes, I see one by Dimitris Kanzas.
Yes, Dimitri, you wanted to hear what the corona is all about. So now yes. You've heard. So your reactions or even objections, even better objections.
First of all, I would like to really thank you because I really enjoyed this talk. And I really agree with the statement that jets are not just fireworks. I think I tried to convey the same message in my talk. Just as a very small comment about why I couldn't reproduce the the X-ray spectrum with the jet component. In fact, this is something I really tried. But the problem is that I'm trying to reproduce a whole radio to even predict some GV emission. And to be able to reproduce the whole spectrum, I would overshoot the X-ray spectrum. So I had to negotiate, let's say, and accept eventually a different component. That's what I call as an external thermal corona. But I have a question, actually. The plot you showed in the middle of your talk, I think it was in the title you said unpublished. It was the time lag yes. as a function of
time lag versus gamma. And for low inclination and high inclination sources.
Yeah, exactly. So that reminds me of the fundamental plane, where they put the radio luminosity as a function of the X-ray luminosity, and they also take into account the mass of the black hole. Do you think that these two are the same, like two different sides of the same coin?
Yes, the fundamental plane is something that we don't really understand. We thought we understood it, but there are these excursions off the main line. So these are the so-called outliers and so on. I don't think this has anything to do with inclination. It's something else. It looks like it, but I think it's something different. I haven't thought much about it, but on the spot, my tendency is to say probably not, but I'll think about it.
Thanks. Thank you very much.
Okay, I see one more question. Oh, two. Okay, so it raised a lot of interest, the talk. That's good. So please, into Kalpa Dihingia. I don't know if I mispronouncing.
Thank you.
Yes, please go ahead.
Very nice explanation and very insightful talk. I learned a lot. Actually, we are also simulating to get the kind of picture you are giving from this. But it seems that when you are referring to the jet, it seems for me like, are you talking about the disk jet? That means wind kind of jet? Or what is your take on this Blandford-Jenai kind of jet?
No, yes, in 10 minutes or 15 minutes, what can I say? And I already said a lot. No, this black hole X-ray binaries, in my opinion, utilize the Blandford-Payne mechanism, and they have which is centrifugal magnetic field and centrifugal forces. The AGN and so the Lorentz gamma are small, 1.5 to 2. However, AGN have huge Lorentz gammas, and I tend to think that it's the Blandford-Nayak mechanism that does that. Now, don't ask me why small black holes use one mechanism and the others use the other, but it cannot be the same mechanism. We have never seen a black hole X-ray binary with a high Lorentz gamma.
Okay, yeah, thank you. But in order to have Blandford kind of wind also, we need a sufficiently strong magnetic field. If that kind of strong magnetic field is present, then the Blandford Janaic mechanism, it will be always present there, right? Or
yes, I agree. You're touching a difficult subject. What creates the magnetic field, the poloidal magnetic field, right? And you know the literature, so I will not tell you about it. There are ideas. The idea that I like, as you see, I like things that nobody else likes. The community does not hear what I have to say. That's okay. I'm not looking for a job. I'm retired, so I enjoy doing things I like. The so-called cosmic battery proposed by Kontopoulos and Kazanas has not been investigated. Has not been investigated. Why? Because nobody wants to look at it. It's the same thing as with the jets. Nobody over these years listened to me about that the jets are important. No one. And so now I rub it at their faces, say, okay, fine. Give me, explain these correlations with your model and I'll be happy. They can't. So again, this mechanism that Kontopoulos and Kazanas proposed needs to be investigated. The magnetic field is produced locally, and that magnetic field then favors the Blandford-Payne mechanism. Okay.
Thanks a lot.